All right. Good evening, everyone. Welcome to our additional Q&A session, 8 o'clock. Wow, you people are my heroes. Connecting to talk about Comporg at 8 o'clock at night. That's impressive, and we have 43 people, so 42 students joined. That's awesome. How you folks are doing? Yeah, I can't help it. Just love to organize computers. That's cool. All right. Could you go over question 8 from the homework? Certainly. So, someone says these sessions are very helpful, and yeah, you're welcome. All right. So, question 8. It is a lot easier than you folks probably think. So, let me open up my whiteboard. Okay. And I guess I need to share it with you. And right, Webex, share. And then I need my chat and Q&A. Yeah, I don't know if we're going to be using Q&A or not. But if you have something for Q&A, put it in there. I will be keeping the Q&A window open. All right. Here is the chat and question 8. All right, so here's what you needed to do for question 8. So basically, you were given 1-bit ALUs. ALU0, ALU, let's say 31 if we are building a 32-bit ALU. And this is result 0. This is A0, B0, and then we have less. So let's call it L0 for less 0. And this one would be A31, B31, L31, and then the output is going to be R1, and of course we have C in and C out for each of those ALUs. C in, C out. And then we have this set signal, which is an output, and it is actually connected to L0. So this is nothing new. This is the design from the textbook. And L31 is just constant 0. Okay, so let's just go back to our zyBooks and make sure that I didn't miss anything and that this is all that we have. zyBooks in the problem. All right, C in. Oh, okay. We need control signals, so we have A invert, B invert, and operation, and then we need overflow. Okay, sounds good. So we have, and I will just combine all control signals into one bus. I will call it control bus. So that will include A invert, B invert, and then the operation bits themselves. So they are all control signals. They are all routed the same to all their, right? So I'm making it bold to indicate that it is actually a bus, right? So multiple wires together, and then we have this overflow, which was a kind of mystery, one of the mysteries that you needed to solve. And so the first problem was exactly to, to decide what this overflow, how to make this overflow signal. And the idea was to analyze like all the cases when we have an overflow, that is when the result does not fit into the number of bits we have set for the values. So the range is outside of the range that we can represent with however many bits we're given. And you would build a table. And then if you looked at enumerating all the possible cases, and then when you looked at the table, you would see that actually thing that sticks out is that whenever C in and C out are the same, there is no overflow. Okay, so let's say we are adding two positive numbers, and at some ALU, the incoming Cin carry into that bit is 0, and carry out of that bit is also 0. It means there's no overflow. Okay, so then you would look into the other four cases, and you would see, oh, actually both of these cases mean it's an overflow. Okay, so if you have an incoming carry of 0, but then the outgoing carry is 1, it means that it's an overflow. Okay, so it's like you are adding positive numbers, and then you end up with a number that has 1 in the most significant bit. So this is all for, of course, ALU 31 case. Okay, because their overflow will only become apparent when we look at their most significant bit. Right? If we look at any other bits, we don't know whether it's going to be an overflow or not. Okay, we can only determine it once we look at ALU 31, or if it's a 32-bit ALU. Right? So those are actually two cases when there is an overflow. And then from this, hopefully you remember that it is just, which gate is it? Which gate do I need? It's an XOR, exactly. So this is overflow, and this is C in, and this is C out. Okay, so that's just the overflow. It's a single wire it's a Boolean function, which is just 0 or 1, whether there is an overflow or there is no overflow. And then, of course, what is it connecting to? So it's here, it's inside this ALU. And the output is connected to overflow. And this is C out, and this is C in. Okay. And then the second part was, all right, so now that I have this overflow, how do I actually fix my SLT instruction implementation so that whenever I have an overflow, the set signal is correct? Because we have, and the example in the problem was exactly when we are doing -7 less than 6, so -7 minus 6, and instead of getting -13, we were getting some positive value, so because of the overflow. And clearly, in that case, we did want set to be 1, okay? Because my -7 is less than 6, but without our original version of their ALU, the one that was given in the problem, was suggesting that this set wire would be at 0, and then of course the result would be 0 instead of 1. So we would not be setting the value of the result to 1, we would be keeping it at 0, and therefore it is incorrect. So that means that we need to kind of have this additional box that would fix that problem. And clearly the problem was related to overflow, so we need to have this overflow fed into this box. And then what would this box need to do? Well, if we think about it, it would just mean that whenever we have an overflow, so here's an overflow, here's our original set signal, and here's our, let's call it set prime, our modified or fixed set signal. So when there is no overflow, there's nothing we need to do with the set signal. It is correct as is. So it's 0, 1, 0, 1. However, when there is an overflow, we just need to flip the set because we see that otherwise it would be incorrect. So if it's 1 and 0, the result should be 1. And if it's 1 and 1, the result should be 0. Okay? So what goes inside this box that I drew here? What do I need to make set prime from overflow and set? Another XOR gate, exactly. So I have this XOR gate, which is just that. Exactly. Yep. And that would fix that problem. And I know many of you spent a lot of time on this problem, and I have a feeling that many of you were overcomplicating this problem. But you see, it's not. It's just a couple more gates. That's it. But of course, you need to think where to put them. So this was really hard to do in open circuits. I feel. Why? Did you have problems with making ICs? So if you make a 1-bit ALU, then you didn't even for the problem we were not asking you to draw a 32-bit thing. You could have done. So we were only asking you to show us the corrections that had to be made. Okay, and so then if you wanted to test it, you could totally do not 32, but like a 4-bit ALU out of 4 1-bit ALUs. That would also be acceptable. But even doing 32 should not be that daunting because you could just copy and paste those blocks. So once you have a single bit ALU as an IC, then it should be maybe a bit tedious to get everything connected, but overall, I don't think it would be too complicated. Yeah, so the way to go was to make a 1-bit ALU, make it into an IC, and then that would be it. All right, so let me go up. So I'll be switching between the chat and just to make sure that I go more or less in the chronological order. So that was a request for question 8, and do you know when the exam grade will be released? So TAs are done with the grades, so I just need to review the grades and release them. So I plan to do this tonight. Okay, is practice exam 5, 6, 8, and 9 answer released tomorrow at lab? Yes, that's the plan. I have drafts. I don't have them, written as full programs yet, but hopefully I have time to do that along with writing the exam itself. Okay, so spent hours starting it and ended up submitting was basically we will do nothing. All right, and I thought question 8 is the MIPS one. I don't know. I don't remember all those numbers. We can look it up. So no, question 8 was the problem that we just went over. It's this textbook problem B24. It's the homework problem. So not. I don't know if I messed it up. No, the person who asked the original topic, the person who asked the original question was asking about question 8 from the homework, not from the practice problems. Does carry in and carry out have any relation to C in and C out in C++? No, not at all. C in C++ means character in. It's a stream of characters that are incoming, and C out is the stream of characters. So C stands for character, not for carry. Okay, and what are the exact slides that we will be tested up to again? Just want to make sure I'm not missing anything. Okay, so let's go over that. So we start with 3A, and in 3A, our last test ended with K-maps. So we continue with 99, slide 99. Well, your numbering might be a little bit off because I was inserting those pop quizzes in my slides, and I might not have updated the PDF with the slides. So it's better to operate not by the slide number, but by the slide name. Okay, because I was not removing any slides, any significant slides. So starting with a slide on ALU, Arithmetic Logic Unit, and all the way to the end of 3A, and then with 3B. So we decided to keep memory for their next time. So from the beginning of their slide deck up until this slide, 8-bit memory is going to be on the next exam. Well, not on test 6, right? Not on our test tomorrow. So for our test tomorrow, we start here with slide 18. So arithmetic for computers, integer addition, subtraction, overflow, and then multiplication and faster multiplication and even faster multiplication. Okay, so optimized is faster, and this one faster is even faster than optimized. And then division, and then the algorithm for division, and the hardware for division, and faster division, which is this. And we don't have an easy way to do an even faster division, unlike multiplication. And then MIPS instructions to do division. Remember that division gives you both their ratio and the remainder. So if you are asked to do a mod operation, which in C would be a percent sign, then you know what to do. You need to do div and then just access the remainder. Okay, because this div gives you both the remainder and the integer part of the ratio. And then, so of course, so this is all going to be on the test tomorrow. So floating point, and then we were discussing IEEE 754 format and standard, and then performing operations on floating points, and so addition. And here's an example of how the addition can be performed. Again, it's completely analogous to how we do it in our familiar decimal system, with just the correction that we only have two values, 0 and 1. Other than that, it's exactly the same algorithm. And then floating point multiplication and instructions to do floating point. To deal with floating point and MIPS, it's getting a little bit more involved because their operations are handled by a separate coprocessor, which we call coprocessor 1, CP1. So you have to move stuff around a little bit more. And actually, I noticed a mistake, a typo in on one of the websites that give you their syscalls for MIPS, and let me try to find it for you because it was, on one hand, it was kind of obvious, but like I had to actually search some other resource to verify that I'm not crazy. All right, so it was, where was it? Here. No, this looks this looks good. F12 and F12. It was in here. Oh, okay. It is the same thing, right? Yeah, it is the same thing. It is this syscall 6. Okay, so it is suspicious. It should be suspicious, right? That the float and double for syscall 7 are returned through general purpose registers. If you look at print float, print double, their value to be printed is passed through F register F12 as it should. But this looks suspicious, right? With V0, it just doesn't sound right. So and then if you Google some other resource, MIPS syscalls, and you look at some other source, you will see that indeed our suspicions were correct. The result is passed back for read float, read double, syscall 6, syscall 7 through F0, not through V0. Okay, so I just wanted to mention it if you are debugging your own problems. Just beware of that. Of course, if you on the exam, if you look at the wrong reference and it says the result is returned through V0 and you write your code assuming that it's indeed V0, of course we're not going to penalize you for that. And if it happens that a TA deducts for this, then just file a grid inquiry and we will refund you those points, right? Of course, it's completely not your fault, not your responsibility that there is a typo in one of their reference materials, right? But it should be, of course, F0. All right, so that was that, but I digressed, and we are back to 3B, and so because their instructions are handled by the separate code processor, things are a little bit more involved. There are more instructions that we have to know, to learn, or to know where to look for them, because we have to do load and store to operate with our F registers, and there are also versions for single precision and double precision, so hence this .s, .d, and there are special comparison. So the whole branching thing is done very differently from our traditional integer instructions that operate on integers on our general purpose registers. So here we have to first compare, which sets a special flag which we don't see, which we cannot touch, but we can indirectly look at it with branch instructions. Okay, so that's that, and this of course is all going to be on the test, and then this code Fahrenheit to Celsius, you have a working piece of code float.s that you can just run, and then this example you also have fully spelled out, fully written, that you can run. So it's MIPS, but just with double values. So their example with temperature conversion uses floats, hence single precision. Their example with array multiplication uses double arrays, hence double precision floating point. So both for both options we have examples, right? So and then a discussion on why it is important to have accurate and reproducible arithmetic. And then this section is also technically included, but it's probably, even if there are questions on this, they're probably going to be very high level, because we only, had a very high level discussion about subword parallelism, and more discussion on parallelism is coming up later in this course. x86, again, we only covered briefly. So this just, the convention of their, just their general understanding of the topic is all that is expected of you, and then matrix multiply, and that's where we stopped. Okay, so starting from slide 73, 74 is going to be on, like I said, starting from this right shift and division and associativity is going to be on their next exam, on the next test. All right, and yeah, and thank you, people are answering, but I think it was still good to kind of go over this. And yeah, Niha is here. It's good. And yeah, Niha, since I while I remember this, some students were saying earlier in the lecture that some of the test 3 grade inquiries are still unresolved. So if you could, please take a look with other TAs at that, and get those grade inquiries resolved. That would be great. All right. Are A invert, B invert, and operations tied to every ALU number? Yes. So those are control signals that each single bit ALU needs. And if you look at their, where's my Zybook, right? So if then you look at their, and it's of course not under problems, but under the main topic on ALUs. Okay, and when we construct their ALU, they're like our larger ALU, 4-bit, 8-bit, 32-bit, whatever, from single-bit ALUs, you see that these blue control signal or signals, right? It's a bus. Typically, operation is, unless your ALU is very simple and only supports 2 operations, you need more bits for operation than 1. Okay, so then it's typically a bus, and you see how it is the same control signals are sent to all single bit ALUs. And of course, if you have A invert, B invert, it would be the same thing, right? As you can see here. So we typically want all single bit ALUs to work in sync, to work together, and they, of course, we want them to perform the same operation. And if we want to invert A, we want to invert all bits of A, not just some bits. So that's why all those control signals are fed in parallel. Okay, pretty much overflow XOR set handles overflow detection. Yes. Okay. And C in, C out. I think I answered that. And XOR. And okay, and someone answered that probably before I answered that. All right, and XOR set is their output that determines their so that we route back to the less signal of their least significant ALU, and it is used in their operation in the mode that we call SLT. So SLT, when our operation, our control signals, operation A invert, B invert, when they select the SLT mode of our ALU, then the result, what are possible results? Well, SLT sets the result. Set meaning it is going to be 1 if one argument is less than the other. And if it's not less, then the result is not going to be set, and meaning it's going to be non-1, not 1. Okay, not 1, we can pick any value. The easiest for us to pick is 0. So basically, we can make SLT work so that it either sets the result to 0 if it's not less than, or 1 if it is less than. But this 0 and 1, they are for the whole bit. So they are at the level of, if it's a 32-bit ALU, of all 32 bits. So what does it mean for, for our value to be 0 with all 32 bits? It means all those result 0 through result 31 are zeros. What does it mean for the number, for the value to be 1? It means that result 0, the least significant bit, is 1. All other bits are 0. So we see that, well, indeed, SLT, in SLT mode, the only thing that would be changing is whether this result 0 is set to 0 or 1. And that's why all other ALUs get 0 to their less input, right? So this third from the top pin, this third from the top input is less. So on the picture above, it was labeled, as you can see here. Because indeed, in SLT mode, those result bits, all result bits except for possibly the very first one, the result 0, are going to be 0. Okay, and then whether this least significant bit result is 0 or 1 is determined by the sign of the result that we perform with the adder, right? Remember, when we do less than, we actually perform subtraction. Then we look at the sign of the result, and if, depending on the sign, we either set or to 1 or set to 0 the result 0, right? That's why we route this set back to our ALU 1. And we can see that, yes, indeed, set is just the most significant bit. This is the MSB, right? So this is a 1-bit ALU for the MSB. This is a 1-bit ALU for all other bits. So we see we only need to know the sign of the result, which is one most significant bit. And this is exactly the set signal right here. Okay, and then we route it to the less input of the least significant ALU. Okay, is that making sense? Yes, set comes from the full adder, right? So even more so, set is actually the result of the adder of their most significant bit, right? So those full adders are the same in all their ALUs, right? In a single bit ALU for their MSB right here, and their single bit or 1-bit ALUs for all other bits, those adders are exactly the same. So we can reuse this part, right? The only thing that changes, so the only thing that we need to add to our MSB 1-bit ALU is this overflow detection, which produces overflow, and we need to route this set signal. Because remember, when our operation is SLT, the operation bits are 1 1. No, not even 1 1. Yeah, the operation bits are 1 1, so it is mode 3. And that means that less signal, which for MSB is 0, is routed to the result. We want the result to be 0. But at the same time, we want to make use of the result of the subtraction that our adder performed between A and B, because the sign of that result, okay, we don't route it to the result bit, to the result output, okay, because the result has to be 0, but we want to use that result, the result of the subtraction, as our set bit. And that's why you see how we take this set bit, the result of the subtraction, the most significant bit of the result of the subtraction, and route it as the output of this MSB ALU. And then we have an external connection that connects this set output to the input of the less of the least significant ALU. Okay, so why XORing C-in and C-out works for overflow again? You just need to look at all the possible cases, like make a table and analyze all the possible combinations and support them with examples. Like one example you already have when you have -7 -6, and then try examples that will not cause an overflow, but both operands are positive. So like try adding 3 and 5, and try adding both negative numbers, but with no overflow in the result. For example, -1 and -1, both are negative, and the result is going to have to be negative, so it's going to have 1 in the most significant bit. But look at their C in and C out, and you will see their what it is, right? So you will see that at the level of their most significant bit, carry in will be 1 and carry out will be 1, which means there's no overflow. You are just adding two negative numbers. Okay, so just by looking at all possible combinations, you should be able to see that their overflow is when C in is different from C out, and this is XOR. All right, can we go over ALUs themselves? So hopefully we just did exactly this. So if there are more questions, more specific question, please let me know. I'm still going through the chat. I didn't know we had to make it into an IC. You didn't have to. It's in reference to that question 8, but it would definitely be a good idea. So it would save you time. And I think I showed how to do that, and I answered a question earlier on how to make ICs in open circuits. All right, and what was set again? I think I talked about it, so let me skip it then for now. And all right, set is just, and more questions about set. So set is just an output from the most significant bit ALU. Okay, and this is this ALU, this 1-bit ALU, and we see that set is just the result of it is taken from the adder. But we know that in SLT mode, we actually want the subtraction to be made. And so if you are in SLT mode, you need to set your operation right, but you also need to set your A invert, B invert correctly so that your adder actually performs subtraction instead of addition. Okay? So SLT in that sense is somewhat similar to addition, but instead of routing the difference of A and B to the result, we set the result to either 0 or 1. But to facilitate that, we need to take the sign bit of the most significant, the sign bit which is the result of the most significant bit, and that's why we take it from the output of the adder. Okay, so this dot here is the sign bit of A minus B. Okay, and then we use that as shown here to determine the value of result 0. Remember, in this mode 3, which is SLT, whenever our multiplexer is set to connect less input to the result output. So for the least significant bit, right? This this less signal is exactly this set, right? This y here. Okay, and depending on, so it's basically the sign of the difference of a and b, and if that sign is 1, it means that this result, which would be result 0, is going to be 1, which means that the overall result, if we look across all 32 bits, is going to be 1. If this set is 0, which means that the difference is positive, which we interpret as the first operand is not less than the second operand. This set signal is 0. The 0 gets here, and then in ALU0, it is connected to result 0. Result 0 is 0. All other result bits are 0. So across these 32 bits, we have just number 0, right? We have a 32-bit number, which is 0, which means we didn't set the result, right? Because SLT says only set if it's less than. If it's not less than, do not set. So we chose to, to keep our result at 0 if it's not less than. Okay, and I'm all right. Flip-flops are on exams. Yes, absolutely, but not on their exam tomorrow. It's going to be on their on test. It's going to be test 6, right? So set is 1 if b greater than 0, if a greater than b, and that's the correct for even the overflow cases. Yes, so SLT should work correctly. So SLT A, B, and yeah, so SLT A, B is result is 1 if A is less than B. Okay, and if A is not less than B, we can choose to put our result to set our result to any other value other than 1. Okay, but of course we want to make our life easier, so we chose to to keep our result at 0, just because it is the minimum effort, right? So it's only 1 bit difference between 0 and 1, so it's the easiest for us to switch between setting or not setting. But that's why, yes, if A is greater than B, we decide to keep our result at 0. And that's correct for even the overflow cases. Yes, and that was actually your question 8 from the homework, because as you can see, this design here is not working correctly for the overflow cases. So your job in question 8 was exactly to fix the design so that it does work correctly even for overflow cases. And I answered already about exam 4 grades. And can you explain optimized division? All right, so let's look at this optimized division. All right, and okay, here we are. Let me see if our Zybooks have a better maybe animated picture of this. It's not under ALU. It's under. So you were asking for division, right? Yeah, division it is. All right, so this is the regular one, and for the optimized. Okay, yeah, there's no animation, unfortunately, but it's not a big deal. We can use our imagination. So let's look at this in comparison with their original algorithm and the original hardware. So here in the original one, and let me play this animation. Luckily, it is available. Okay, so we have our divisor, which we are shifting right. Okay, and because of that, since we are shifting right, roughly 32 times, we have to make sure that this register is large enough so that we can keep our divisor in, within the range of this register. So it's just, effectively it's a register. And then we are shifting our quotient left, and with a quotient, we don't really, care if we lose bits, right? Because we only use them once, and then we use this ALU here in the middle to, to do our partial sums. So if you look at this example, right? So we will be performing our sums, right? So, but some of them have negative value, but it's still a sum, right? So subtraction is essentially the same, and so we have this 64-bit ALU to perform this. Okay, and this is the register where we keep our intermediate results. Okay. And of course, with the original algorithm, they all have to be, 64 bits, right? So the divisor is technically 64 bits. Yes, it kind of travels. So initially, it's 32 bits, and it travels through this 64-bit register from left to right. But it will go from being flushed from being placed flushed left in this register to being flushed to the right. Okay, and therefore we do need 64 bits. And since we are summing something 64 bits, we need to have a 64-bit ALU. The result, of course, is also 64 bits. That calls for the remainder register to be 64 bits. And the optimized version is just making changes that allows us to use a 64-bit wide register for the remainder, but then only use 32 bits for the ALU and the divisor. So basically, instead of shifting the divisor, we are, shifting their value in this remainder, in this, kind of partial result. Okay, and we shift it left and right, and so their ALU and quotient register are 32 bits wide now, and only their remainder register needs to be 64 bits. Okay, why does it have 64 bits? Well, because the result is actually the quotient itself, 32 bits, and the remainder, 32 bits. So the information that we end up with when we are dividing is 64 bits, right? 32 and 32. And you can think in terms of the division instructions and MIPS, right? So if you look at those, you will see that, oh yeah, we still have that, low and high registers. One contains the ratio, the other one contains the remainder, but those are two pieces of information that result from the division and 64 bits, so there's no way around it. And of course, if we don't need the remainder, for instance, yeah, it's fine, but this information in principle is there. So that's basically it. All right, so it's the same algorithm, slightly modified to shift a different part of the partial result. That allows us to save on the width of the quotient register, and because of that, we can now use a 32-bit ALU. Note how the ALU dumps its result uh, into 32 most significant bits of this remainder register. So this arrow here, it goes to their higher part, right, to their senior part, to the senior half of this register. And when we take this partial result and feed it back to ALU, we also only take that partial result. And of course, as we shift the value in this register, so we can we thus form the result. All right, and so I don't think that they give you any kind of more complicated algorithms. So this is for their traditional, non-optimized division. So this is for optimized division. They don't give any additional examples. They don't tell you exactly how and when this remainder register is shifted left and right, and that's why I don't expect you to know this. I don't want really to make things more complicated than they already are. And if you're interested, I will be glad to tell you more. But just to be clear, it's not something that you will need to know for their upcoming tests, right? Because it wouldn't be fair. If it's not covered in their textbook, it wouldn't be fair to expect that all of you would have interest in this topic and would want to know more. All right. And there's a Minecraft clock. Yeah, I yeah, probably should look into that. I actually have, believe it or not, I have never used Minecraft. So I heard a lot about it. So maybe it's time. All right. What are the C1, C2s in the instruction names, and what are the differences? So C1 is coprocessor 1, and that's the only coprocessor for now that you need to be worried about. Don't worry about C2. Its time will come later. Okay, so for now, C1, if you see C1, you know it's coprocessor 1, and you know it's floating point. So you can actually look at our favorite green card, green reference card, and so let me point out a few things here. So first, now we know what this whole section means with floating point stuff here, and you know branch and division and addition and subtraction for floating point. And so you see BC1T, right? So it's branch on coprocessor 1 condition flag being true, right? So this condition flag is denoted as FP cond. You cannot, like I mentioned, you cannot directly read it, but you can perform actions based on the state of this condition flag. So, and that's really all that we need. So, right, we want to branch depending on whether this flag is 1 or 0. So here C1 is coprocessor 1. It means it's our floating point coprocessor, right? And then all their a couple other places where we see the C1 load word, load double word. All right, so things like that. But in this section, some of the stuff we see relates to integer operations. So we see that MF high, MF low. So move from high, move from low. So high and low are two registers that are used to store their you know to deal with the result of integer multiplication and division. Right. So for example, mult. Right here we have high low is set to the result of multiplying two general purpose registers. Okay, and the same would be for division, except for there one would contain their ratio, the other one would contain their remainder or modulo. Okay, so that's for integer arithmetic. All right, and then the other stuff that is worth mentioning is so this is the formula for IEEE 754 standard and how it represents values. Okay, and then yeah, single precision, double precision formats. So it's very unlikely that we will ask you to do any double precision formats manually. Okay, so of course it may come up in MIPS programs for sure, but it really makes no sense to torture you with, setting 52 bits of the fraction manually. All right, so 23 bits is more than enough for you to suffer. Well, I'm kidding. Of course we don't want you to suffer, but there's probably going to be a question on converting or representing their values in IEEE 754. Okay, so that's probably something that should be expected. All right, and that's pretty much it. So don't worry about CP2. We will talk about it's another coprocessor, right? Essentially, but we will talk more about what it is and how it is used later. All right, there was one question in the Q&A. Let me see if it got answered. How does MIPS round floating numbers? Well, it's not easy to answer this question because it is possible to interpret this question in several different ways. So one way to interpret it would be, if I have a value, a 32-bit value, and I just move it from a general purpose register into a floating point register, is there a conversion? And the answer is no. So, if you have a value like a hexadecimal value, like 0x and then 8 hexadecimal digits, and you say it's already in IEEE 754, then you just move that value to your desired F register. There is no conversion, there is no rounding. When performing operations on floating point values, the rounding happens according to the algorithm of the corresponding operation. So, for example, we had an example here. Here, see how the result that we got had more, and it's not IEEE 754, it's close, but it's a little shorter, right? It's just 4 digits example. Okay, but you see how, and it's decimal, but like I said, it's the same idea that will be applied to our binary operations, right? You see how the result does not fit the number of digits we have set, and that's why it is rounded as part of the operation. So it kind of happens by the hardware that performs this operation, be that multiplication or something else, right? And then the result is written as an IEEE 754 number. And then there is another dimension that I should mention, and that is there are conversion instructions. And if you looked at practice problems, we introduced some of those instructions there. They are very simple. That's why we didn't really spend any time talking about them separately, but occasionally they are useful. And those are instructions that allow you to take an integer like, I don't know, 25, 10, and convert it into a floating point number. Okay, so those conversion instructions are available, and if we on their exam, if we want you to use them, we would probably mention that here are some useful instructions you might want to use, right? So just pay attention to those hints. And in this case, of course, if the number cannot be represented exactly, then it will be represented with some error. Okay, we discussed previously that depending on what you are converting to what, you might not be able to represent numbers exactly. And it's not only for floating point numbers. So can someone tell me, and I'm going to scroll in the chat so that I can see your answers. Can someone tell me what is the largest number that we can represent a signed integer? So the largest meaning the largest positive value that we can represent with 32 bits. And you don't have to be exact, but roughly, what that number is. Well, it's hexadecimal, uh, 4 billion. Okay. Well, for signed, it's not 4 billion. Yeah, it's 2 billion roughly. Okay, so then my next question is that number in, yeah, so someone actually computed it. Okay, cool. So how many significant digits does this number have? 7? Why? This number that uh, uh, Shui King posted, 2 1 4 7 4 8 3 6 4 7. How many significant digits does this number have? 10, exactly, right? So there are 10 valid digits. Each of them matters. Okay, so now I'm asking you, if we attempt to represent this number as a single precision floating point, will we be able to represent this number exactly? Why or why not? No, and the answer is no. And if I ask you why, their answer is a single precision floating point is able to give us 6 or 7 significant digits of precision, and we have 10. So that means that, and I'm just trying to find it in the slides. It should say, yeah, this is the slide. So it's approximately six to seven decimal digits of precision. So that means that this number, 2,147,483,647, will be represented probably as something like 2.147843 times 10 to the third. Okay, or 484 times 10 to the third. But you got the idea. We will keep however many digits we are capable of keeping, 6 or 7, and then we will just choose the value that would be the closest. It's probably going to be 147 484, and then just triple zeros. Okay, just because we don't have 10 digits of precision, 10 decimal digits of precision at our disposal with a single precision arithmetic, with a single precision IEEE 754, which is our traditional float data type. Right. So the number that we will represent is going to be an approximation, and it's, if you think about it, it's going to be not even that close. It's going to be like at least 300, 350 off from the number that we really want. But that's the price that you have to pay. There's no magic, right? If you want to represent big numbers precisely, you cannot do floating point. They have a wide range, so the range can go up to, for single precision, 10 to the 38th, right? But we cannot represent large numbers precisely down to every single unit. So for numbers, like this, it's going to be approximate. So if you're converting an integer into the floating point, you actually may lose precision. And this is something that you need to be aware of. This is actually something that has very clear practical consequences in your everyday programming practice, right? So you have to be aware of that. And when you're performing conversions, so back to where we started with the conversion instructions and MIPS, there's no magic, right? It will do its best, but it does not. It will only do what it can given the single precision. If you are converting an integer to a single precision format, you may lose precision. Okay. With a double, that's not going to happen, right? So integer to double is going to be converted without loss of precision, just because double, as you can see, has 16 decimal digits of precision, and our largest integer has only 10, so we should be good here. All right, so does step 4 do round up or round down? So let's go back to this question. Oops, multiplication, floating point. So the short answer, it depends. Okay, it depends on their algorithm, and it depends on their hardware that performs this algorithm. So this algorithm is not going to be in software. This algorithm is going to be in hardware. Okay, so it depends, and yeah, you have to look at the capabilities of your particular processor and hardware. So no easy answer, right? Okay, and how does MIPS round floating numbers? So hopefully I covered that. Okay, and then let me go back to where I was, and we still have more than an hour, so that's good. Hopefully I can go over everything. I just want to just go in some order. Okay, so C2, yeah, it was a type on the slide. We found out during the lecture, and I corrected it. So that's why you were asking about C2. Yeah, it was a typo. Will clocks be included in their exam? Sure, because we spent a great deal of time on them even before today. So we had more clocks today, but even before that, we had clocks earlier. So yeah, they may show up on their exam. Okay, and I'm going through the chat. Can you go over the register conventions for FP registers? Like which registers do we use and when? We didn't really talk about it, so it's pretty much Wild West. So use registers those registers any way you like. Okay, so for F registers, yeah, it's Wild West. One thing though that I wanted to point out is that if you look uh, at our syscalls, and we already discussed that this one is buggy. Okay, but you will notice that the result is often returned through F0, and their arguments are often in F12. So you can use it to your advantage. So for example, if you read a float, the result is in F0, and then you can start just performing your computations in F0. And at some point, if you want to store the result, you may want to store it in F12, so that if you then need to print that result, you don't need to move anything anywhere. Your F12 already contains the result, and you just need to set V0 to 2 and do a syscall. Okay, so try to optimize, but other than that, I don't think there are any rules. All right, can I do a short demonstration on binary multiplication of these two? Certainly. And all right, and yeah, so we have what 1 1 1 times 1 1 1, 1. Okay, so we have 1 times this, so it's 1, 1, 1. Okay, and then we have this 1 times this, we have 1, 1, 1, 1, and then we have 1, 1, 1, 1. And please check me doing this to make sure that I don't mess it up. All right, so it's 1. So 1 and 1 is 0, and we have 1 that is carried over. So we have now 1, 1, 1, and 1. Okay, so 1 and 1, 1 plus 1 is 1, 0. So plus 1 is 1, 1. Plus 1 is 100. So we have 0, and then 10 is carried over. So it's 1, 0. So now we have a 1, 1, 1, and 1, 0. Okay, so we can do
Hello,
10.
Professor. Sorry to interrupt. I think we need another line of ones because there are like
Thank you.
404 ones.
Yes, you're correct. You are correct. Thank you, Neha. And all right, so let me get rid of all of that and fix it. So it's going to be 1. Yeah, it's a lot of ones that you requested. All right, so it's 1. This is 0, 1. All right, so maybe, all right, so 1 plus 1 is 1, 0. Plus 1 is 1, 1. Plus 1 is, so I'm summing this. So it's 4 ones. 1, 1, 2, 3, and I need one more. So it is going to be 101. It is going to be 101. Did I do it right? So 1 is carried over. So 1, 2, 3, 4 ones. So 1, 2, 1, 2, 3, 4. Right. So I think I got it. So 1, and then this is going to be carried over. How does 1, 1 plus 1 equals 1, 1, 0, 0 work? All right, so 0, 1, 1 plus 0, 0, 1. Okay, 1 and 1 is 1. 1 is carried over. 1 and 1 is 1, 0, 0. 1 is carried over, and it's 1. So it's 1, 0, 0.
And since we have so many ones, so that is why we are having. So the third line where you just did 101, that should be the next one. This is just 4 ones, so this should be 100. So 0 and carry over 10.
Okay, so let me see. Thank
So
you for
first
help.
one is 1 plus 1, that is 10. So that is already 2 ones, and we forgot to count the first one.
All right, so this is 1, this is 0, and 1 is, so this third bit, is that 4 ones?
Yes, that's just 4 ones, so that should be 100, right?
1 and 1 is 1, 0, right?
Yes.
This is 1, 1. This is the second one, so it's 11.
That's the third one, right? The first 1 plus 1 is 2 ones, no? Which is giving me 10.
Yeah, 1 plus 1 is 10.
So that's 2 ones already, and then we add another.
Oh, okay. You're right. You're right. I'm messing this up. So, and I think I had it correct the first time around. So, this is 1, 2. Yeah. So 1, 2, 3, 4 ones, and it is 100. Thank you. Thank you for helping me. Hopefully get this right. So this is 4 ones, so it is 0, and 1, 0 is carried over. So now we have 4 ones, which we already know it's 100, so we can just reuse this result. and we are adding 1, 0. So it's 1, 1, and 0. So the result here is 0. And so it was this. Let me draw some separators to help it. All right. So, and we have into this, we have 11 as the carry out, right? So now we have 3 ones. So it is 11 and 11. All right. So 1 and 1 is 0, 1, and 11. Okay. And so the result is 0. And here we have 1 and 1 incoming carry. So we have 1, 1 and 1, 0. So it's 1 and 101. All right, so it's 1 and incoming is 1, 0. So we have 10 and 1, it's 11. So it looks like this is the result. Okay, does that make sense? And yes, thank you, Niha. You are very helpful. It's very nice to have someone check everything that you write. All right. So that was that, and let me go back to where I was. Okay, so question 5 from their practice exam. Okay, let's take a look. What was that? Okay, so yeah, this is their probably one of the longer MIPS programs where you just need to to write the code to perform the computation according to their algorithm, right? So it is going to be recursive. So you get to practice what we learned before, but now with floating point numbers, right? And we actually say double precision values. So and like I said, I don't want to just disclose their solution because I want you to actually write that code and practice that code. But I will, as we discussed in the lecture, I will let you know the solutions tomorrow. I want you to try and do this yourselves. That's the whole point of the practice. If there are any questions that you're not, you please feel free to ask, right? So I'm willing to answer like any specific questions about how this is done, or if you are not sure, how to proceed. But overall, first you need to set up their program so that it asks the user for their sides of the matrix and then enters their values. So, and I give you their output, their the sample output. And then you need to call this. So you need to decide how to store it, and that's probably where you need to think a little bit. What would be the best way, knowing what their computation that you will need to be performing afterwards. So probably for initially, you just want to store it as we were storing our two-dimensional arrays earlier. So just row by row. But then, of course, you will need to go through the first row and take the value and then recursively call the same determinant procedure on a smaller matrix, right? On a matrix that is obtained from the original matrix by crossing out the ith row and the jth column, right? Where I is 1 in this case, and j would go through, well, I would be 0 if you're using 0 based, of course. So j would be 0, 1, 2, 3. Okay, and then whatever that determinant recursive call returns, you multiply it by this. Okay, and so all in all, at the first call to determinant, we'll spawn 4 recursive calls because we need to compute the determinant of M11, M12, M13, M14, and that's the basis of the recursion. So then the question is, how do I, how do my recursive calls get the matrix that they operate on? And there might be several possible solutions. If you don't have any better ideas, a pretty straightforward approach would be just to make this matrix as a new array. So basically, allocate space. The size is going to be 1 less than the original size. So if our original size was 4 by 4, then this minor matrix would be 3 by 3. And then just copy the values into this new matrix. Okay, you know that you need to copy everything except so basically you need to copy this part. All right. So for M11, that's M11. Right. So just physically copy it. Right. It's probably not going to be the most space efficient, but it's probably the most straightforward approach. Okay, and then when you call this determinant procedure for M11, just give the address of this new matrix, and then you can discard it, you can keep it. It's not that important what happens afterwards. Okay, so hopefully that's the idea is more or less straightforward, right? Why does MIPS have 32 dedicated FP registers? Offloading point use that much more than every other type of data that we need, 32 of them, and only 8-ish saved registers. Well, we have, for one, we have 32 general purpose registers, right? So it's only, a few S registers, right? But we have 2 registers and more, and A and V, okay? And then remember the 32 registers for floating point becomes 16 if we talk about double precision. So 16 is not that whole lot, okay? So and yeah, that's probably the minimum that we need to be comfortable writing programs and avoiding the necessity to dump values into memory all the time, because memory is slow and it takes an additional instruction to store something in memory. What happens? What A invert or B invert is different for each ALU? So it's in reference to this uh, question here. So B invert is something that we discussed in detail, right? This is something that we need to perform operations like A minus B. So why would we need A invert? Well, maybe we want to also perform an operation like B minus A. Okay, so that might be an option. We might ask you to actually design an ALU that does B minus A and A minus B. It's totally possible, right? So, but we, one of the things that I mentioned before, here in this design, A invert and B invert are different control signals. You might be asked to kind of combine them, kind of produce them yourself from the operation code, right? So this operation code might be, 100, and you might need to produce A invert and B invert out of a single operation code. Is that clear what I mean? Yes, no, maybe? I'm looking for some feedback in the chat. Is anyone still awake?
Sorry, can you repeat that?
Okay, sure. So let me actually grab a screenshot so that I can draw on it. So one easy question on their exam would be, can you please build a table that shows their OP, their operation codes, and give the description of the operation? Right? So that would be an easy question. So can you tell me operation codes and description? Please go ahead. You can just unmute yourself and go ahead.
0, 0 is and.
Good.
0, 1 is or.
Cool.
And then 1, 0 is addition, is the adder.
Okay.
And then 1, 1 is undefined.
Yeah. So unused, not NA, unused, whatever. Right. What about subtraction? I don't see subtraction here.
You would set the B invert to 1 and set the carry into 1.
Okay. So we need to factor in Cin. We need to factor in, A inv, B inv, right? So with a C, so for and, let's complete then the table for these for this control signals. Well, carry in is not a control signal, but it still plays the role, so we keep it in this table. So for and, what do we do with C in?
It doesn't matter.
So it's an X, right?
Yeah. Unused.
We call it don't care. Don't care. It can be 0, can be 1, doesn't matter. And A and B, A inv and B inv,
They have to be 0.
they have to be zeros, right? So for or, well, it's the same, right? For add, that's where things get interesting. So what about Cin?
0.
0. A invert, B invert,
Also zeros.
also zeros. All right. And then unused operation 1 1, which means it doesn't matter what we use here. Hey, what about subtraction? We lost subtraction. Can our ALU do subtraction? And if so, how do we get it done?
It'd be 0, 1 for A and B invert, and then 1 for C in.
1. So 0, 1, and 1. Okay.
And then 1, 0.
Yeah, and we call this sub. Okay, exactly. So you see how add and subtract share the operation code, but we can still distinguish between them because, yeah, we know B invert, C in have to be different. So that is exactly this is just comes straight out of this circuit diagram. As a next step, we might ask you, all right, can you please reshuffle this A a little bit, right? This A invert, B invert is kind of clunky. So, but yeah, we have to support at least these operations, these 4 operations. So can you reshuffle this ALU, redesign it a little so that we have the following? We no longer have A invert, B invert, and we don't want to be bothered with setting Cin ourselves. All we want is a single. So basically, we want to get rid of this, and so we want operation to be 0, 0, 0, 1, 1, 0, 1, 1, and of course we can shuffle the order, saying like or, and then add, and then sub. Okay. So there, of course, the condition is this is what we want, okay, and just take this circuit and make minimal changes to make it happen. Okay, what would be their and of course carry in stays, all right? So there's nothing we can do about it, so it's fine. But the idea is to get rid of those clunky A invert, B invert. So how would you do that? Well, the approach is Well, we actually keep this design, right? But we make A invert and B invert. So A and B are still inputs, carry out is still an output, result is still an output. Operation and carry in are still inputs, but A invert and B invert are now kind of internal signals, right? We do not expose it to the outside, and we add some circuitry, like some black box, that takes operation, takes carry in, and produces A invert and B invert internally, so that the user, has this very nice interface. Oh, there are just 4 codes for 4 operations, and that's it. Everything is very straightforward, and you need to design this black box that produces A invert and B invert appropriately according to their code of the operation. Okay.
So
Yep.
the
Go
black
ahead.
box takes the operation and they carry in as the selectors of like a multiplexer, say for instance.
Yes,
Or
and of course you will need to redesign this, this multiplexer, right? So it will have this third input now, of course, right? Because there are now 4 operations that this multiplexer will be switching. Okay, so you will need to think what to put here. But yeah, the idea is to have minimal changes. Basically, you are redesigning the interface of this ALU. Okay, so instead of having operations encoded like that, right, where there is really an operation in our original thing, you see there's no difference between add and sub, right? So I might even write add sub, add sub, right? Because it's really kind of the same operation code 10. Okay, and then within that single code 10, whether addition or subtraction happens is determined by additional control signal B invert, and that's a valid design. But for the end user, I might argue that, well, it's easier for them to go with this more streamlined design where subtraction has its own operation code. But if we don't want to make too many changes, the easiest thing is to just design the black box that would produce those, A invert, B invert, and obviously, unless we support B minus A, we don't really need A invert. So right, this can go away unless you are asked. Right, so this sub, if we just tell you sub, it's not clear what it means, right? For add, it's clear A plus B is the same as B plus A, all right? So we have the commutative law for addition, so it's clear. For sub, it's kind of ambiguous. We have to tell you whether we want A minus B or maybe we want B minus A, right? So both are subtractions, right? And they're not the same, right? Subtraction is not commutative. So, depending on whether we are asking for A minus B or B minus A, you want to, produce, B invert or A invert, but then you still need to set their values of all inputs to something. So if you decide to kind of, cross this out, then stop and ask yourself, all right, what do I have this input connected to? Previously, it was an external pin that imagine it's like an IC that you give to the user and it's their problem to connect all inputs. But now if you're saying A invert is an internal signal, you cannot just leave it in the air, leave it hanging, right? You have to connect something to it. So you would decide, oh yeah, I still need this A invert, even if it's like a constant 0, right? Maybe you connect it to well, it's not a very good notation, but you can just say, oh, it's going to be constant 0. Okay, so it's fine. Maybe that's that's your use is that's what you need this A invert to be. right? But then, of course, the question is maybe, you don't need this inversion of A to begin with, and you can just get rid of this whole thing. But if you're not asked to do that, don't do it, right? So just make sure that you use their existing hardware appropriately by generating the correct signals, right? So this can, the zero can be just a constant zero, or it may be generated by your black box. But all inputs of all circuits have to be connected to something. With there are some extensions. Like if you're not using the fourth input of the 4-input multiplexer, like we would not use it here, we would not even show it here. But that only works if we can guarantee that operation is never 1-1. So this heading unused input is never connected to the output. Okay, and it would still be safer to connect it to something, right? It would be fewer undefined signals in your circuit, which is always good, right? So even if you don't use it, just connect it to 0 or 1, whatever you see a safe default is going to be. All right, so that's that, and let me see. Can we go over how to convert to and from the normal numbers? All right, so let's do that, and go back to our slides 3A. So there was actually another bug, believe it or not, and not in only not
slides.
just in our textbook, but yeah, I'm not going through the correct part. Not just in our textbook, but in some of the tools, including Mars, if you used its floating point tool. All right, so and it is exactly related to the normal numbers. So in the version of the slides that you probably have, it just says negative bias, right? It doesn't say 1 minus bias. And so it's not that hugely important because it's a typo in many tools and even in our slides. So if you did it with, if you followed this incorrect formula, which has 2 to the power of negative bias, we will not deduct points for that, okay? Because of course there's no way you could know, you trust the slides, and so that's it. That's why I didn't really mention it in the lecture, but I probably will. So how do you, first, and a few students noticed actually. So how do you verify? Well, the ultimate truth is the standard, and it's not that hard to find. At least, like the latest version, I couldn't find. They're available for free, and I think it's a 2019 version. I couldn't find it, so IEEE wanted to charge money, to allow me to download the standard. But their 2008 version, which for our intent, for all of our intents and purposes, is exactly the same, right? There are no major differences. So you can see it's a 2008 version. I was able to download the PDF, and if you look at the standard, you will see. And it's probably too small, but you can see that, yeah, it is actually B, which is 2, right? B is the base of their system, 2 times 1 minus P, okay? So, and then P is their number of digits. So if you, and E min, so that's the other thing, right? E min is actually defined in one of the definitions, I think, a couple of pages up. E min is the minimum exponent, and E min is 1 minus E max, and E max is coming from this table. E max is 127 for the single precision. So long story short, it is 1 minus 127. Okay, so and bias is 127 in our notation, so it is 1 minus bias, not just negative bias, right? So, and the amazing thing is, if you look at your Mars and you go to their floating point thing, you can actually notice that things do not really click into place. So here's our denormalized number. The exponent is all zeros, and we have this. You see that it says. So let's put some ones here. So let's put 1 here. And you see that it still says the exponent is 2 to the negative 127. In fact, it is 2 to the negative 126. Okay, and the probably my hypothesis is why they got confused is because there's this dot 1 here. Dot 1 is exactly 1/2. So if you factor in this dot 1, right, it's 2 to the negative 1. So if you multiply 2 to negative 127 by 2 to the negative 1, right? So it's like you had negative 126, you subtracted 1, you end up with 2 to the negative 127. Okay, so it's quite easy to get confused because there's this 2 to the negative 1 sitting here. But you can see that this is incorrect, and you can actually catch exactly why and how it is incorrect if you do the minimum number that is distinguishable from 0 and is representable. So this is that number. Okay, so you see this is 1 in the lowest significant bit of the fraction. So then the question is, how many bits do we have here? We know it's 23. What is the weight of this bit? It's negative 1 and negative 2 and so forth. So the weight of this bit is negative 23, is 2 to the negative 23rd. Okay, so and if then we do our math here, I have a fancy calculator, so we can do 2 to the negative 23rd times, and if we trust what the tool tells us, times 2 to the negative 127 time to the power, not times, 2 to the 23rd times 2 to the negative 127. So if we do this, we see the result. It's 7 something 10 to the negative 46. Okay, and we see that hey, that's not the value that you tell us, right? Because you tell us 2 to the negative 127 plus this fraction, which is 2 to the negative 23rd, and it does not, it does not make 1.4. So we actually have to multiply your result by 2 to get 1.4 to the negative 45. So the value, this value is correct, right? But it does not match what they write here, because it's not 127, it's negative 126. So if we go back and correct our formula, then we get exactly 1.4 times 10 to the negative 45. Okay, so but in any case, that's you don't have to worry too much about it, because we will accept either 127, negative 127, or negative 126. And for the other than that, I don't think there are anything particularly interesting happening here for the normal numbers. So you have, the normal numbers. You know that it's a denormal number if the exponent is all zeros, and then you immediately know that the hidden bit is 0, which means that instead of having something like something like 1.1101 whatever, where we say, oh, this is always 1, so this is hidden, we don't have to store it. But when we recover it, right, so we only store this part, but when we recover it, right? We write this fraction, and then remember the difference between the fraction and the significand. So this is the fraction, and to recover the significand, we write this 1 point here, and this becomes the significand. This is for normalized numbers, right? For subnormal numbers or for non-normalized or denormalized numbers, it's different. So there is no hidden bit. So if our fraction says this, right, it is this, right? There's no hidden value. So it is just 0.1101, right? So you to compute what this value is, you would do like 1/2 plus 1/4 plus 1/16, right? There's no hidden one. Okay, and yeah, that's it. So you compute their decimal value of their significand by just doing 0 plus fraction, so just taking the fraction, and then you multiply it by 2 times -126 for the case of single precision values. Okay.
Are the lecture notes fixed of like these errors, or are the current lecture notes with the errors?
So let me check. I think I re-uploaded the PDF. So their error was in the PDF, right? So I think I re-uploaded it, but I will re-upload it once again to make sure that all their most recent corrections have been done. So yeah, I will re-upload it right after our session. Okay, and so we have about 15 minutes left, and yeah, I didn't go through everything in the list, but if there is anything of particular importance, so I think I covered the Q&A, 2 questions on the Q&A, didn't cover everything that we had in the chat. Was there anything that many people were asking for and I kind of missed in the chat? Any requests? So let me scroll all the way down so that I am looking at their most recent chat messages. I'm confused about storage for double arithmetic. Would add .d f6 f6 f12 be stored in f5 f6? So this is there is a very easy answer, and I'm not just going to give you the answer. I'm going to direct you to the slide that actually shows that, so that if you print that slide or if you memorize the slide, you will know. And it's down the instructions. So all registers for double precision are pairs, and the pair is always an even numbered register and the next one. So it's F0, F1, then F2, F3. Okay, so it's going to be F5 and F6 and F7. Okay, and you only need to, in the instruction itself, you only need to mention the first register in the pair, so the even numbered one. So we should probably have an example here with array multiplication, because with matrix multiplication, yeah, because it's a double, and you can see that yeah, you have you indicate F16, right? You don't tell that, oh, it's a pair, right? It's just F16, F18. So you just name the first register in the pair, and it will automatically know which pair to use. It's going to be F16 and F17, and it's going to be F18 and F19 because it knows how to make those pairs. Is denormalized just the decimal part of their number? No, in denormalized, well, why do we have denormalized or subnormalized numbers? Is because the number is smaller than the smallest normalized number, but we can still represent it. Okay, so in this case, we can kind of relax the requirement for all numbers to be normalized, And because it is a small number, like it is very close to 0, clearly we only need to do that for numbers that are smaller than their smallest normalized number. And that's why their exponent is actually negative 126, right? So it's pretty much the lowest exponent that we can have. How do you check for not a number? There's a very easy thing that you can do. You can just look at their hexadecimal value. So if we go all the way up to, and yeah, recall homework 4, right? How did you know that some value is infinity? You just convert it to hex, and then you can compare it like that. So let me see where we are. Okay. So, like, this hexadecimal value, you know what it represents, right? And if we go with infinities and nans, come on. All right here. Okay. So you know how they are encoded. Okay. So you can just go by that. Okay. And shouldn't it be 2 to the negative 2 to the power negative 22 instead, as we start with 20 until okay, so back to the normal numbers. Okay, so here and here, you see the dot, right? The dot is the dot. It separates their integer part from the fractional part. So the weight of this bit is going to be 2 to the negative 1. Always, right? Because it is the next to the dot. It is next to the right from the dot, from the point. Okay, so this one would be 2 to the negative second, and so forth. So the weight of this one right now is 2 to the negative 23. 2 to the 0th would be this bit to the left of their point, which we don't have it, right? Because we don't need to store it, right? Because we can always get rid of it. If we have 1 point something decimal, we can always shift our point and make it point something. So we can use our exponent. We can shift our point and account for this using our exponent, so that we don't have to worry about storing their integer part. And if we have normalized numbers, then we do have this integer part. It's exactly this hidden one, right? This hidden one is to the left of their point, and it has their weight of 1, 2 to the power of 0. But in denormalized numbers, we have no hidden bit, and therefore we don't have any integer component in our fraction, and that's why that's the difference when we recover the value. So when we want to get the decimal representation of IEEE 754 encoded value, for denormal we say 0 plus fraction, whereas for normalized numbers we have 1 plus fraction. 1 plus fraction, right? It's exactly because we have this hidden 1, and this hidden 1 is, as this slide shows, is to the left of the point. All right, it's this 1 point something that is a hidden one. All right, and let me now scroll down. Wait, why is normal negative 127? I thought it was 1 minus bias, which is, well, bias is 127, so 1 minus 127 is going to be negative 126. So, G, you are correct, but it's negative 126. Yes, but you're correct. Okay, and let me see what else. We have a few more minutes. Yes, if you can express all the numbers so if you're dealing with numbers that are powers of 2, don't mess around with division and multiplication. If you need to multiply or divide by a power of 2, just shift them. And even or odd, it's very easy. You just need to look at their list a significant bit. If it's 0, the number is even if it's an integer. Of course, if it's not an integer, then even odd doesn't really make any sense. Q9 in the practice problems. Let me see what we have for Q9. Okay, yeah, SQRT. Yeah, so any way you like, you can actually compute SQRT algorithmically if you want to. You can tabulate it. You can use an instruction. Really, different ways to do it. So, but yeah, I probably should have added a hint here. So I guess for the practice problem, it's okay, right? So you can explore a little bit, but for the exam, I probably should have added a hint. Yeah, so in is 1 for sub because we need to invert all bits of B and then add 1, and we do that by abusing the in input, right? Because it artificially injects the one that we actually need. Can you go back over a fraction that has a denominator that is not a power of 2? So you mean, all right. So for now, yeah, let me take another one real quick. So for normal numbers, though, it's exponent negative 127, though. The exponent, if as it is stored in your 32-bit number, which is IEEE 754, if the exponent is all zeros, it's a special case. Okay, if it's non-zero, right? Well, for 1, we know it's always non-negative, so it can be 1, 2, 3, and so forth. And you just subtract the bias, so it's exponent minus 127. That is correct. Yep. And what's a good way to load zeros into double precision F registers? I would say probably the easiest way would be to use the conversion instruction to convert 0 into the double precision value. So it's just one instruction, right? So you can convert integer 0 into double precision 0. All right, so and let me finally get back to that question. A fraction that has a denominator that is not a power of 2. So do you mean like converting a fractional value into encoding it into an IEEE 754? Okay, something like 131.33. So let's do exactly this as you wished. All right, so we have 133. And please remember, the values that we give you on their exam are going to be somewhat artificially easy, so that you don't need to use a calculator. Okay, and so that that might not be the case here, obviously. So I might need to use a calculator here because it's just an arbitrary example. But on the exam, since we do not allow you to use calculators, of course, we're not going to be expecting you to adding values like 2 to the negative 32nd plus 2 to the negative 64th, something like that. Okay, so 133. So well, first this is 1, right? So this is 2 to the 0, this is 2 to the 1, 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, and so forth. All right, so the way we do it now, we need to have this 0.33. Okay, if we put 1 here, it would give us 1/2. Okay, 0.5. That's way too much. Okay, so exactly. So we need to take 0 here. Okay, so now next question is, do we take 1/4 or not? So yeah, we take 1/4. So now what's left is 133 minus 1. Well, let me use the calculator. I know I could do this manually, of course, but just for the sake of time. So we do 133 minus 125. So we have 0.08 that we need to take care of, right? So 2 to the negative third. So this is 1/8. 0.125. Too much. We don't, right? We would overshoot our value. So no. So then, and for brevity, let me just write -4, -5, -6, -7. All right. So then 1/16, 0.06. Okay. So that works. All right. We can take it. So that's that. So now we have 0.08 minus 0.065. 0.08 minus 65. And I'm left with 0.0175. And then, so, and then we just go on and on like that. So it's probably not going to be an exact representation anyways. Okay, so, but let's do one more step. So we have 1 divided by 32, that's 0.03. No, that's more than we need. So we don't take this fraction. So next is going to be 1/64. That's going to be 0.015. So I think we take this. All right. And yeah, so there's still going to be, some remainder, and we can just, keep going until we have enough bits. So in single precision, we're going to have here until, until -23, basically. All right. So, but let's stop here. We're going to have some error, but it's pretty inevitable. It just, if you were doing this for real, you would go all the way up to 2 to the -23rd. All right, this algorithm. We're just going to stop here, and I assume the rest are zeros. It's not going to be the most precise representation. We could have done better if we went all the way through. All right, and so now, is this normalized or not normalized? Well, it turns out that this number is, this value is already normalized. So we just take this as our fraction. Right, this is what we call fraction, and our exponent, we didn't shift anything, so our exponent is 0, 2 to the power of 0. So we have, so what do we need to store? So that when we subtract 127, we're gonna get 0. So we're gonna, yeah, 127. and then sign is going to be 0 because it's a positive. So, and 127 is 1 less than 128. So 128 would be 1 and all right. So 7 bits. So let me count the weights. 1, 0, 1, 2, 3. Come on. 0, 1, 2, 3, 4, 5. This is 32. This is 64. So one more 0. Right. So that would be 128, and we need 1 less. So it would be this if I did my math correctly. How many ones did you get? 7? I think I got the same. All right. So there, this is sign, and then we have 8 bits. So 0, 1, 1, 1, 1, 1, 1, 1, and then all right. So we can kind of put those for now. So this is sign. This is exponent, and this is fraction. Is going to be 0, 1, 0, 1, 0, 1, and all zeros, right? So a total would be 23. Okay, and then we, to turn it into hex, we would regroup this thing so that we just split by 4 digits, 1, 2, 3, 4, right? Ignoring the boundaries between the fields, so just cut it like that, and encode each nibble, each group of 4 digits with a 1 hexadecimal digit. And and of course you're not going to be able to do this on the exam, but as you're practicing, as you're preparing, you can check it here. So our exponent was 1, 2, 3, 4, 5, 6, 7, and 0, 1, 0, 1, 0, 1. Okay, so we get rid of this. Oops, and we have 1, 2, 3, 4, 5, 6, 0, 1, 0, 1, 0, 1. And indeed, we see that we got something close to 1.33, right? So not exactly, but maybe if we went further, we would of course get closer. All right? Does that make sense? All right, cool. You're welcome. And yeah, sorry, I'm 7 minutes over our time. It's getting late. So thank you for all of you who stayed so late, who attended this session. Hopefully it was useful. And yeah, be cool. There's nothing to be afraid of on the exam tomorrow. But still, best of luck to all of you. And please torture your TAs and mentors tomorrow during your lab sessions. Right? Thank you, folks, and have a good night.